Welcome. It's a pleasure to be able to present to you today the work that was done on achieving reliable cold weather tertiary nitrification with novel biocatalysts. The work was conducted by Microvi in conjunction with Thames Water's innovation team and was started in June 2018, completing in May 2019. It's a delight to be able to present these results to you. Firstly, let me introduce you to the Microvi microniche engineering platform technology. The mechanism we use is to create a synthetic microorganism material composite called a biocatalyst. That material composite is developed to create the perfect environment for which a microorganism can reside, proliferate, and perform to its best ability. We choose specially selected but naturally occurring microorganisms and retain them indefinitely inside the biocatalyst itself. In that way, we're able to divorce sludge age from microbial population, allowing us to maintain a particular population of organisms that are there relevant for the particular applications. These applications can cover everything from ammonia through to BOD to phosphorus to numerous different applications. Effectively, in traditional treatment, these organisms are present. However, they may not be there in sufficient numbers because they're outcompeted by the fastest growing ones. They may be more efficient than those that are the fastest growing ones. However, because they're outcompeted, they're not there in significant numbers. The Microvi technology takes those particular organisms, intensifies them, and places them inside this perfect environment, which allows them to be successful in the application that they undertake. The Thames Water, who are the largest UK water utility and approximately the fourth largest in the world, have a number of tertiary ammonia removal processes in their asset base, installed typically 10 to 15 years ago. They have consents ranging from 1 milligram per litre up to 3 milligram per litre, which these nitrifying systems have to achieve. During the course of the operation of these systems, Thames Water have established a number of operational issues that they've had to overcome and are therefore looking for alternative treatment processes that overcome these issues inherently. So Thames Water worked with Microvi to establish a pilot program in order to assess the MNE technology and start to look at things such as process responsiveness, operability in terms of simplicity, its load response, and in particular its temperature response, where they'd seen a number of treatment assets struggling during low temperature operations that are experienced periodically during the winter time in the UK. Also wanted to establish the design limitations in order to allow full-scale comparisons and also to undertake dissolved oxygen response testing in order to establish the energy impacts. It's fair to say that a lot of tertiary ammonia systems on the market today either have to operate at very, very high dissolved oxygen levels to achieve performance, or themselves do not control dissolved oxygen effectively. So these were part of the studies that were to be undertaken during the trial from June 2018 through to May 2019. Representative Thames Water site was selected for conducting the pilot study. The site itself was an existing trickling filter plant of around about 5,000 population equivalent. The site itself was fitted with nitrifying sand filters as a tertiary process, thus allowing the Microvi process to be compared directly with an existing operational system. The process on site consisted of headworks, primary tanks, rock media trickling filters, humus tanks, and then the nitrifying sand filters. The feed for the Microvi system was the feed for the nitrifying sand filters and would be typically 10 to 30 milligrams of suspended solids and between 1 and 6 milligrams of ammonia. The expected temperature range was between 7 and 20 degrees C. This typical asset represents the asset base across Thames Water to where this technology is typically provided, and therefore would give Thames Water a direct look of how it would look and feel if the Microvi process was successful and how it could be applied across its wider asset base. A brand new pilot plant was constructed for this particular study. The pilot plant consisted of 2 reactors, each of 2 meter cubed in volume. The reactors themselves could be operated either in series or in parallel. For the majority of this study, they were actually operated as 2 separate parallel reactors, allowing testing of different dissolved oxygen concentrations, for example. The reactors themselves are relatively straightforward. They're a single pass system, influent coming in at one end, effluent leaving at the other end. The reactors themselves are of a sufficient height to allow good oxygen transfer and not be compromised by any scale-up issues that are sometimes associated with reactor height. The reactor itself was fully instrumented with instrumentation on the inlet for ammonia and turbidity, as well as nitrate and nitrite. Each reactor was fitted with ammonia, dissolved oxygen, and pH, and the effluent was fitted with turbidity. The design flow was between 2 and 12 meter cube per hour, giving hydraulic retention times of between 0.2 and 2 hours themselves. The aeration system was fine bubble diffused aeration and can be controlled using conventional dissolved oxygen set point control. Mechanical mixers were fitted that could be operated independently of the aeration system, allowing you to turn down the airflow to the reactors and not compromise the mixing of the system. The entire system was fully automated and it could also be remotely accessed and operated, thus allowing full flexibility in terms of control and undertaking different operational cycles. The biocatalyst utilised in this particular project was the Microvi biocatalyst, an organism that has been selected for its efficient removal of ammonia, but also BOD, either simultaneously or independently. Typically, the biocatalyst has a nominal diameter of 5 millimeters. 587 kilograms or 1,250 pounds of biocatalyst was added to each reactor, giving a packing density of approximately 27% by volume. This biocatalyst was actually manufactured in 2015 and held in storage before being transported to the UK and utilised in this particular project. That's one unique factor of the biocatalyst and the Microvi technology, is ability to manufacture and store for considerable periods of time before being utilised in its application. The pilot plant was commissioned on the 21st of May before operation began in the first operating mode on the 4th of July. We ran a number of different operating modes. The first one was declining flow, although that was related to the fact that the influent pump would clog periodically, resulting in the flow slowly dropping over the course of a 1-week period. That was cured with the installation of a variable speed pump on the 4th of December, which allowed us to run at continuous fixed flow for an extended period. 28th of February represented a period where we moved to much higher flows to test the hydraulic retention time capabilities of the system before moving to a diurnal flow pattern, a flow pattern that matched the existing works influent, before moving to the high diurnal flow testing on the 28th of May 2019. Interspersed in these operational modes were periods of shutdowns and startups, as well as different levels of dissolved oxygen testing in order to understand how responsive the system was to these different applications or aspects of operation. Now let's talk about the results. Firstly, let's have a look at the temperature that was being received during the course of the pilot study. Here in the green dots is the online temperature readings from reactor number 1, measured off the scale here on the right hand side. As you can see, the temperature ranged from approximately 20 degrees C down to just above 10 degrees centigrade. There were a couple of areas here and here where we saw very low temperatures, but they were during pilot plant shutdowns where there was no incoming flow and the reactors were exposed to the ambient conditions, leading to a significant drop in temperature inside the reactors themselves, but they were not representative of the sort of performance of the system. Whilst we didn't receive the temperatures as low as 7 degrees C that we experienced previously, although that was a result of an extreme weather condition called the Beast from the East that happened in 2017. However, 10 degrees centigrade was relatively typical of UK water temperatures, and in fact are typically the design basis for most of the water companies in terms of their ammonia requirements. When we look at the actual influent and effluent ammonia, this is the readings from the lab data that was taken by Thames Water using composite samplers. The blue dots here represent the influent ammonia, and you can see range from relatively low, just above 1 milligram per litre, cropping up to around about 4.5 milligrams per litre. When we look at the final effluent or the effluent from the pilot plant, we here have the red dot, which is the effluent from reactor number 1 only. When we look at the little grey dots here, that's from the lab data for the combined effluent from reactor 1 and reactor 2. The majority of time the reactors were run in parallel operation. And then there are a few samples for reactor number 2 showing again very good performance. As you can see, most of the performance is below 1 milligram per litre. In fact, most of the time the effluent sample is coming back from the laboratory with at the limit of detection, which is 0.05 milligrams per litre. Now, as I mentioned, the pilot plant had a number of online instrumentation. When I overlay the online ammonia monitors onto the system, you can see the performance in a little bit more detail. Here in the purple dots, we actually have some influent online ammonia. Previous to this point in here, we were utilizing an ion selective electrode for the influent ammonia. Given the very low levels of concentration in the influent, it was proven to be unreliable. So we relocated one of the wet chemistry monitors from reactor number 2 onto the influent to give us a more reliable data set. And as you can see here, that during this period of time, there was a spike in influent ammonia up to around about 6 or 7 milligrams per litre coming through. The yellow dots here represent the ammonia levels in reactor number 1. Showing again a similar performance to that experienced during with the lab data. There were a couple of periods here and here where you can see high ammonia in that reactor. These were effectively due to plant modifications in one instance where the pilot plant was shut down, and then the second one was when we lost the mixers and the blowers for that reactor as a result of a power loss to those particular components. As you can see, when we rectified this, the effluent levels recovered very quickly. You will see a slight increase here in ammonia effluent concentration, and that was as a result of us moving to effectively a high flow period. As I mentioned, we had a high flow diurnal profile period, and that's the period of time when we moved to that situation. Again, when we look at the results coming through across the entire period, you can see the effluent performance under normal operation to be less than 1 milligram per litre, and most cases less than 0.5 milligrams per litre, indicating very good performance across the entire range of temperatures that were experienced during the course of the pilot study. Breaking these results down a little bit further and then comparing the performance of the Microvi pilot against the existing nitrifying sand filters. Here we have broken down the data into temperature bins between 5 and 10 degrees here, going up to between 20 to 22 degrees here. The pink boxes represent the influent, the green boxes represent the nitrifying sand filter effluent, and the blue boxes here represent the Microvi effluent. As you can see during the course of the study, whilst the ammonia levels in the influent were relatively low, you can see the difference in performance between the nitrifying sand filter and the Microvi effluent. As you could have seen in the previous graph, the Microvi effluent was always less than 1 milligram per litre, more often than not less than 0.5 milligrams per litre. Again, this is represented in the data at the different temperature ranges. And it also showed that there wasn't significant variation of performance during the study across the different temperature ranges. That's not necessarily true of the nitrifying sand filters, which is one of the reasons why the study was undertaken in the first instance. And you can see there is a deterioration in performance in the nitrifying sand filter effluent during the colder temperatures. Again, this demonstrated that Microvi itself was able to manage performance across the temperature ranges, which is exactly what Thames Water were looking to try and understand across that particular study. When we look at the performance data in a little bit more detail, utilizing the online instrumentation and taking a 1 week period during the diurnal profile testing, here we have the influent flow rate, and you can see here the diurnal profile pattern that was put in place, peaking extensively around about midday, declining and then increasing again to represent the late afternoon, early evening spike before dropping off extensively during the nighttime flow. The ammonia influent here, utilizing the wet chemistry probes, and we understand these to be very reliable. You can see again a diurnal profile which sort of matched that, but lagged the influent flow rate by about 1 hour or so. But it was representative of what we were seeing. As you can see in the blue here, this is data taken every minute you can see there is a trend that follows in the effluent of the ammonia concentration. But again, looking at the data set here, everything less than 1 milligram per litre. This was done at an average hydraulic retention time of 40 minutes, although during the diurnal flow spikes, that would drop down to less than 20 minutes in terms of the hydraulic retention time. Performance again demonstrated very well. Here you can see there is a period where ammonia in the influent does increase up to around about 8 milligrams per litre, with performance still being maintained below the 1 milligram per litre throughout that entire period. In order to help us develop the design parameters for full-scale applications, it's useful to normalize the data set. In this case, we're normalizing the amount of ammonia loaded per meter cubed of reactor volume per day, and then applying that against the final effluent concentration. We're able to demonstrate that there is a linear relationship here, whilst there is some scatter in the data, and that's related to the fact there is so much data being generated in 1 minute intervals. But you can quite clearly see that a design curve is being developed here, which shows that for around about 0.4 kilograms per meter cube per day of ammonia loading, you would expect to see an effluent concentration of anywhere between 0.3 and 0.4 milligrams per litre in the effluent. This type of graph really helps support our understanding to what level of reactor volume you would need for any given ammonia load coming in, and independent of hydraulic retention time. Part of the study was to understand the responsiveness of the Microvi system to operational events. Well, one of these events was an extended shutdown period of 6 weeks for reactor number 2. Prior to bringing the system back online, the entire pilot plant was shut down for 2 days. A partial drain down was undertaken on both reactors, as well as the mixers and the blowers being shut down. During that period, there was an overnight temperature drop, and we actually froze the surface of each reactor by about 1 inch, but no impact on the actual biocatalysts themselves. Both reactors were then brought back on service at a 1 hour retention time. Here is the information following that 6-week shutdown for reactor number 2 and the 48-hour shutdown for reactor number 1 on the restart. The influent ammonia here is in the green line, reactor number 2 is in the orange line, and reactor number 1 is in the blue line. As you can see, reactor number 1, even after a 48-hour shutdown and a freezing condition, came back online very, very quickly. Reactor number 2, however, being offline for over 6 weeks, did take a little bit longer to come back down, but once it did, after a period of say 7 or 8 days, was back under good performance as it was previous to the shutdown. This demonstrated the ability of the Microvi system to be able to sustain long periods of shutdown and then be brought back on service relatively quickly. One of the objectives of this study was to understand the performance of the process to extreme flow and load changes. One of these events is represented in the graph here today. Here we can see the influent ammonia concentration in the green following the diurnal profile. But more interestingly, here in the yellow line is a rapid change in flow rate, typically from less than 1 meter cube per hour straight up to 5 meter cube per hour, that was done instantaneously as a result of a pump switch point. As a result of this, you can see that the load represented in the grey line increases from less than 0.05 kilogram per meter cube per day up to 0.35 kilograms per meter cube per day. So a significant increase in a very short space of time. Not unsurprisingly, the final effluent ammonia did see a corresponding step change, although it went from less than 0.05 milligram per litre up to 1.49 and then quickly declined again back to less than 0.5 milligram per litre in a very short space of time. This can demonstrate the ability of the process to absorb relatively high and extreme flow and load changes to the system. Just to summarize the overall performance comparison between Microvi and the existing nitrifying sand filters. Here we're presenting the influent and effluent data from both the systems. One thing to note out is the differences in BOD and suspended solids removal. We didn't expect the Microvi process to remove any solids, unlike the nitrifying sand filters, which it did do. And that was represented during the trial, where you can see that we achieved pretty much zero removal of suspended solids. A small amount of BOD removal that's associated with any residual soluble BOD was achieved, but not to the same extent as you would achieve in a solids removal process, such as the nitrifying sand filters. The biggest difference here obviously was the performance in ammonia, where Microvi achieved over 95% removal, whereas the nitrifying sand filters struggled to achieve 70% removal. And this is against a backdrop when you look at the specific loading applied over the entire period. The Microvi system was loaded at almost twice that of the nitrifying sand filters, yet seemed to achieve a significant performance improvement against the system. So that demonstrated that in a like-for-like comparison, the Microvi process outperformed the nitrifying sand filters, both in terms of long-term performance, but also in some of the responsive curves that we saw. So, drawing some conclusions from the results of the study, it was demonstrated that the Microvi process could outperform the existing nitrifying sand filters for ammonia removal, even at higher specific loading rates. And the whole process demonstrated 0.4 kilogram per meter cubed could achieve an ammonia concentration of less than 0.5 milligrams per liter at the 95th percentile. The process also demonstrated that it was robust under performance shutdowns and startup conditions, giving it some great potential as potential storm treatment. The process also is relatively simple, single pass with no backwash or generation of solids during the course of the study, although it was not expected to see a huge amount of solids being generated for these levels of ammonia concentrations. In previous studies, the Microvi biocatalysts demonstrate to have a very, very low level of biosolids production during the conversion of either BOD, COD, or ammonia. But as expected, there was no solids capture from the process. So if there is a tightening of suspended solids consent, it may be necessary to couple the Microvi process with a downstream solids removal system. The whole system could generate very, very low levels of ammonia at cold temperatures and at very short retention times, typically less than 20 minutes. And as a result, the Microvi technology can be considered to be viable for achieving low levels of ammonia, especially in the conditions of variable flows and loads and low temperatures. With that, I'd like to say thank you very much for taking your time to listen to us. If you have any questions, then please feel free to contact us and discuss them. I look forward to hearing from you. Thank you very much.